Welcome to This Explainer. Today, we are diving straight into a fascinating journey right to the very center of the atom. We're going to build your foundational knowledge of atomic physics because, honestly, understanding the structure of matter is the absolute bedrock of radiologic science. Getting a solid grip on this will completely change how you view the physical world around you. We've organized our journey today into 5 quick steps. We'll start with centuries of discovery, then take a look inside the Bohr atom, break down nomenclature and combinations, tackle radioactivity and decay, and finally wrap things up with the types of ionizing radiation. Let's get right into it. Step 1. Centuries of discovery. It is pretty wild to think about how humanity slowly solved the mystery of what makes up the universe. I mean, for hundreds of years BC, the Greeks literally thought all matter was just made of 4 basic substances: earth, water, air, and fire. That was it. Fast forward way ahead to 1808, and John Dalton comes along with a model where elements were these identical atoms linked together in a sort of iron hook affair. Then, by the late 1800s, J.J. Thomson gave us the surprisingly delicious-sounding plum pudding model. He visualized negatively charged electrons as the plums just stuck in this shapeless blob of positive electrification. And finally, in 1913, Niels Bohr introduced the miniature solar system model. Now, obviously, modern quantum mechanics goes a lot deeper today, but the Bohr model is still the absolute best, most practical way for us to picture the atom in our field. Moving right along to step 2, inside the Bohr atom. So, let's zoom in. Here is a totally mind-bending concept. The atom is essentially empty space. I know it's tempting to visualize an atom as this dense, tightly packed, buzzing beehive, but that is a huge oversimplification. Just keep this scale analogy in your head. If the massive nucleus of a uranium atom was the size of a standard basketball sitting in front of you, the orbital electrons wouldn't be buzzing right around it. No, they would be 7.2 miles away. And scattered across all that massive empty space are just 3 fundamental particles. Way out there in the orbital shells, we've got the electron, which carries a -1 charge and has essentially 0 mass. Then, clustered right in the center, we have the nucleus. That's made up of protons, which have a positive charge, and neutrons, which have 0 charge. And because those heavy protons and neutrons are tightly packed together, that tiny little nucleus actually contains over 99.998% of the atom's entire mass. But wait, that brings up a really critical physics question, right? If basic electrostatics tells us that opposite charges attract each other, why on earth don't those negatively charged electrons just spontaneously crash right into the positively charged nucleus? Well, it is all about perfect balance. That strong electrostatic attraction pulls the electron inward. We call that the centripetal, or center-seeking force. However, that inward pull is brilliantly, perfectly balanced by the outward force created by the electron's own velocity. Think of it exactly like a race car taking a super sharp turn. The sheer speed of the car pulling it outward is balanced by the force keeping its tires anchored to the track. That precise balancing act is what keeps the electron flying safely in its specific electron arrangement. And this delicate balance dictates electron binding energies, which is basically just the strength of an electron's attachment to the nucleus. Electrons in the closest shell, the K shell, are bound the tightest. Just look at the massive difference between a small carbon atom, which only has 6 protons, and a massive tungsten atom with 74. The larger and more complex the atom, the higher the binding energy for electrons in any given shell. This is a game changer for us because it takes significantly more energy to ionize a really large atom like tungsten, which, by the way, we use as targets in X-ray tubes, compared to a smaller atom. All right, step 3, nomenclature and atomic combinations. So, how do we practically label all these unique atoms? We use a standard atomic nomenclature, basically a chemical shorthand. Right in the center, you've got the chemical symbol, which is usually a 1 or 2-letter abbreviation, like Ba for barium. Down to the bottom left is the atomic number, or Z. This is crucial because it tells us the exact number of protons, and that number entirely determines the element's chemical behavior. Then, right above it, you have the atomic mass number, or A, which is just the total head count of protons plus neutrons. Now, these ISO terms are definitely going to pop up on your exams, so here is a fantastic little mnemonic device to help you keep them all straight. Isotope has a P in it, so that means atoms with the same number of protons. Isobar has an A, meaning the same atomic mass number, A. Isotone has an N for the same number of neutrons, and isomer has an M, which stands for metastable. That just means the atom has the exact same proton and neutron count, but it's sitting in a different unstable energy state. Now, atoms rarely just chill by themselves. They primarily bond in two distinct ways to form combinations of atoms and chemical compounds. First, we have covalent bonds. This is when atoms literally share their outermost electrons. It's like two hydrogen atoms beautifully sharing their single electrons with an oxygen atom to create water. On the flip side, we have ionic bonds. This happens when an atom completely gives up or gains an electron, which creates a stark imbalance. The resulting positive and negative electrostatic charges strongly attract each other, locking atoms together, like sodium and chlorine snapping together to make table salt. And here is why this matters to us. Those invisible atomic bonds have a massive macroscopic result. Atoms combine via covalent and ionic bonds to make molecules. Then those molecules combine in these vast, incredibly orderly schemes to create human tissues. It's one continuous, deeply interconnected chain running from the microscopic Bohr atom straight up to the exact human anatomy that you will be imaging every single day in the clinic. Which brings us to step 4, radioactivity and radioactive decay. So, what happens when an atom is unstable? Well, radioactivity is defined as the spontaneous emission of particles and energy in order to become stable. Some atoms just exist in an abnormally excited state. We call them radioisotopes, and they absolutely have no choice in the matter. The nucleus literally must spontaneously emit particles and energy, completely transforming itself, until it finally reaches a state of stability. But how do they actually pull that off? There are two primary emission methods. Beta emission is super common. Basically, an electron is created right inside the nucleus and gets ejected at super high speeds, while a neutron actually converts into a proton. It's a pretty neat trick. Alpha emission, however, is way more violent and really only happens in much heavier radioisotopes. In this case, the unstable nucleus just violently ejects a massive chunk consisting of 2 entire protons and 2 entire neutrons, all at the exact same time. So how fast does this radioactive material disappear? That's defined by the radioactive half-life, or T1/2. This is the exact amount of time required for the quantity of radioactivity to be reduced to exactly 1/2 of its original value. You see, radioisotopes don't just vanish overnight. They decay at a decreasing mathematical rate. The amount halves, then that new half halves again, and so on. Which means, theoretically, the quantity of radioactive material never quite reaches absolute zero. Finally, we've reached step 5, types of ionizing radiation. Let's categorize the actual tools you'll be managing in your clinical practice. On one side, we have particulate radiation, which includes those alpha and beta particles we just talked about. Notice that they originate directly in the nucleus, they have actual physical mass, and they carry electrical charges. But then, look at electromagnetic radiation, which includes gamma rays and X-rays. Notice the zeros? They are entirely massless and uncharged. And here's the real kicker. While gamma rays are emitted directly from the nucleus, X-rays are uniquely produced outside the nucleus, out in the electron cloud. Grasping that core distinction between the two is exactly what enables us to safely produce diagnostic images. We have covered a ton of ground today, journeying all the way from the philosophical elements of the ancient Greeks to the precise mathematical reality of binding energies, half-lives, and electromagnetic radiation. So I want to leave you with this final provocative thought to ponder. How will harnessing these tiny, completely invisible atomic forces allow you to clearly see inside the human body and ultimately save lives? By mastering the structure of matter that we've explored in this explainer, you literally hold the key to radiologic science. Thank you so much for joining me, and keep questioning the incredible universe around you.